Okay, next we will talk about the expectation and the variances. So let's first talk about expectation. Expectation is about when we have a given random variable, how do we expect that to happen? There are several possibilities, and if we can only use one number to guess what's going to happen, we won't have a number, and the expectation is one number. Okay, so suppose that we have a discrete random variable x, and the sample space is x1, x2, blah blah up to xn, and we have a probability function that is given to us. So we know the probability for each value to occur. Then we define the expected value, or mean, or expectation of x to be the following. We use the notation mu to denote the expectation of x, or we use this expectation function capital E with a weird script. Okay, then we use this expectation of x to be this one. So what's this? This is a summation of a pair of xi and its probability, the product of xi and its probability. So what does that mean? That means for all the possible values, we use their probabilities to do a weighted average. So that means if I'm going to guess one number for the random event, then I'm going to say that I know there are several possibilities, but some are having higher probabilities, some are lower. So I'm going to weight those possible outcomes so that for the values with a higher probability, I'm going to give it a higher weight. Okay, so that means if I may only guess one number, I would guess the expected value, and that's because the expected value can minimize the average error, roughly speaking. Okay, so let's see some examples. So example 1 again, let's roll a dice. So suppose I have a dice where the probability function, okay, this is just probability function. So the probability function is that 1 over 6 for all possible values. Then the expected value of x is here. Is that we going to take each value and multiply that value by its probability. So it's going to be 1 times 1 over 6 plus 2 times 1 over 6 and so on and so on. And eventually it gets to this, and the expected value is 3.5. We can see that 3.5 is in between all the values, right? It's at the middle of 1, 2, 3, 4, 5, 6. And that means if I can only use one number to express capital X, if I can only use one fixed number to express capital X, I'm going to call it 3.5 because it lies at the middle of all the values. If I have an unfair dice like this, okay, I still have 1, 2, 3, 4, 5, 6, but small values have higher probabilities to occur. In that case, if I calculate the expected value for y, for 1, the probability is 0.2, okay? And for 2, the probability is 0.2, and so on, and so on, and so on. I'm going to get 3.15. Here we can see 3.15 is less than 3.5. So why is that? Well, the reason is simple. Basically, when we are choosing one number to represent all these 6 numbers, we also consider its probabilities. Okay, and because small values has higher probabilities to occur, so the expected value would shift to the left to represent the fact that the outcome is more likely to be a small value. So that's why we expect y to be smaller. We expect y to be smaller. Okay. So similar to expectation and probability, we have a concept called conditional probability and conditional expectation, and that can be very helpful if we have a sequence of events to happen. So suppose that I sell orange juice every day, and that capital D be my daily demand. I know the demand is going to be affected by the weather. If it is a sunny day, then I'm going to have 2 possible outcomes. If the demand is low, it's 50. If the demand is high, it's 250, and both events probability is 1/2. If it's a rainy day, then I'm in a bad situation. If the demand is low, it's 10. If the demand is high, it's 50. And again, 1/2, 1/2 as probabilities. Then these probabilities are called conditional probabilities. That means conditional on something. I'm going to have a probability distribution. Okay, like here. Given that it's a sunny day, I'm going to have a distribution that is 50 for 1/2 and 250 for 1/2. Given that it's a rainy day, then it's another distribution. Okay, so then what is my expected daily demand given the weather condition? We know that given a sunny day, the expected demand would going to be 150. Why is that? 50 plus 250 divided by 2, right? Actually, we are doing an expectation because we weight those possible outcomes by their probabilities. It's just that they are 1/2, 1/2. And for the rainy day, the expected value would be 30, obviously. Okay, these are called conditional expectations. So now, how may we join all these things into one number? It depends on the probability for a sunny day or a rainy day to happen. Suppose that the sunny day probability is 70%, then my tomorrow's expected earning or the tomorrow's expected total demand would be this. I'm going to have the probability of sunny day times the expected conditional expectation under a sunny day plus the other one for the rainy day, okay, which is somewhat intuitive. So with probability 70%, I expect 150. With probability 30%, I only expect 9. Then I have another weighted average, and altogether I get 114. Okay, so this is my final expected demand. The two events we say here are dependent, so that means the weather is random, and the demand is also random. And we say the two events are dependent because the realization of one event, say the weather, affects the distribution of the other, say the demand. Okay, so that means they are dependent, they are not independent. If two events are independent, then the realization of one event do not affect the distribution of the other event. Okay, let's see another example, which is inventory decisions. Recall our inventory problem. We know the unit purchasing cost, we know the selling price, and we know the distribution of daily demand. Suppose that now, instead of finding an inventory level to achieve a certain service level, now I want to maximize my expected profit. Okay, I certainly know that I don't want to order too many, I don't want to order too few, but where is my best inventory level that can maximize my expected profit? Well, that can be done mathematically, but here we're going to use an easier way. I'm just going to try all the possible actions, and for each possible stocking level, 0, 1, 2, 3, 4, I'm going to ask what's the expected profit under that particular decision. Then I can just choose the stocking level with the highest expected profit. Okay, so the concept is simple. I have 9 options. For each option, I want to calculate the expected profit. Then I choose the one that can maximize my expected profit. So let's try it. Suppose y is 0. Then obviously I'm going to sell nothing, but I also don't need to pay anything for procurement. So my cost and my revenue are both 0, so my profit is also 0. If y is 1, then I need to do some calculation. I know with probability 6%, I'm going to have no demand, and then in that case my profit would be -2 because I earned nothing but I paid $2 for procurement. With probability 94%, x is going to be greater than or equal to 1. And I don't care about whether the demand is 1 or 2 or 5 or 8 because I only have 1 unit on hand. So in any way, I'm going to sell 1 unit and earn $10. So in that case, I earn $8 in total. And then I have two outcomes, right? Either x is 0 and I get -2, or x is greater than or equal to 1, I get 8. So my expected profit would be this one. -2 times 6% and 8 times 94%, I get $7.4. That means pi of 1 is 7.4. If I have inventory of 1 unit, if I decide to purchase 1 unit as my inventory, my expected profit is 7.4. Similarly, if I set y to be 2, what's going to happen? With probability 6%, I'm going to again earn nothing. But now because I buy 2 units, my profit would be -4. With probability 15%, okay, 15% here. With probability 15%, I'm going to get 1 unit of demand. And then I earn 10 minus 4. With the other probabilities, with probability 79%, I'm going to sell 2 units because the demand is at least 2. In that case, I earn $16. So my expected profit would become this one. Again, a weighted average of all possible outcomes by their probabilities. Okay, then I can earn $13.3. So if I keep doing so for y equals 3, 4, 5, 6, 7, and 8, I'm going to fully derive the expected profit function. And then I can just pick 1. And then it's not too surprising that the optimal stocking level in this particular example is 4. Okay, so I have shown you how to get the numbers for pi 0, pi 1, and pi 2. And by repeating that, we will see other numbers, and we can see that pi 4 is the highest. Okay, this curve obviously fits our intuition because we don't want to order too many, we don't want to order too few. And turns out that 4 is optimal. But of course, we know 4 happens to lie exactly at the middle of these 8 numbers, right? But this happens to be the outcome when the parameters are given in this way. If the unit production cost is not 2, or if the sales price is not 10, or if the distribution changes, then obviously this curve will change, right? But as long as we know probability, as long as we know the concept of expected profits, then we can always carry the calculations and find the optimal quantity to buy or to store. Okay, so that's how we use probabilities to help our decision making. Thank you.